Welcome everyone to the next iteration of the IITE seminar series. So today it is my great pleasure to welcome Evan Johnson. He is mostly a coexistence theorist, but I've met him in person and I can attest to the fact that it's very good to talk about all sorts of things with him. And today we're going to be hearing, well, of an ecological topic, and it is going to be prevalence of cycles and chaos and complex dynamics in natural systems. So without further ado, Evan, the floor is yours. Thank you.
Thanks very much for that introduction. Okay, so if you go out into nature and estimate abundance for many years, you can draw out these ecological time series. And a characteristic feature of these are these fluctuations, big fluctuations that seem to be, although not all the time, kind of random. And there's three underlying processes, classes of models, if you will, that can explain these. So the first on the left is an attracting equilibrium. You might look at this and say, well, it's bouncing all over the place. Where's the equilibrium? And the idea here is that there's a push and pull between the attracting force of a stable equilibrium and noise or stochasticity, which we normally think about as climate fluctuations. Things like really cold winters, hurricanes, really rainy springs. The second process in the middle is predator-prey cycles. These are self-explanatory. And then third on the right is chaos. Now, chaos looks a lot like the attracting equilibrium, except a lot of the variation in abundance is not caused by noise, but rather severe density dependence, interactions with the focal species or with other species. So you overshoot carrying capacity, and then you undershoot it, and you keep doing that in this irregular fashion. And there are also a few pedantic caveats. First, chaotic dynamics can also look cyclical, so it's a set-subset relationship. Then there are also excitable or episodic systems, where there's an outbreak that looks like a predator-prey cycle, and a refractory period until the next cycle or outbreak can happen, but then some sort of external catalyst is necessary to start the next outbreak. The only example of this, the only real empirical example I know of this, is mountain pine beetle. And then there's also quasi-periodic systems, which is a superposition of cycles where the quotient of frequencies is irrational, but that probably never happens in ecology, so we're not going to worry about it. And these aren't just three random things. These dynamical behaviors, the attracting equilibrium, the cycles, and the chaos, are all connected via the concept of time-delayed density dependence. So in the 1970s, Sir Robert May published this famous paper showing that a very simple model, the logistic model, could generate all three types of behavior as you increase the growth rate parameter R. Now, it's a simple model, but throughout the latter half of the 20th century, ecologists studied far more complicated models and found similar bifurcation diagrams. And if you sort of look at the characteristic of all those bifurcation parameters across all those models, you'll see that the R parameter here is just a metaphor for time-delayed density dependence. It could be a predator attack rate. It could be the maturation time in a stage-structured population. So why care about cycles in particular? One is that they're cool. I probably don't need to convince anyone here about this. But I think, when you go out into nature, it's very clear ecosystems are idiosyncratic. When you look at data, there's a ton of noise. And if you start from that perspective, then you see the regular oscillations of predator-prey cycles. It does seem a bit miraculous. And they're also partially responsible for the existence of academic ecology as we know it. Umberto, this Italian fellow, got his hands on some fish market data and found that during and a little bit after World War I, the predator fish tended to increase in abundance, presumably because of the war efforts, their prey were not being hunted. And then a little bit after World War I, abundance has started to decline. Now, whether this was the return of fishing pressure or a transient predator-prey cycle, he gave his data and ideas to his son-in-law, Vito Volterra, who went on to co-invent the most famous equations in ecology, the Lotka-Volterra equations. So the state of the art in detecting population cycles is the Ornstein-Uhlenbeck state space, or OUSS test, courtesy of Luca and Dobley in this 2015 ecology paper. And the Ornstein-Uhlenbeck model is just a simple continuous time null models that says there are no cycles. The test also relies on a Fourier transform, which says that any time series can be decomposed into a weighted sum of sine waves. And a popular way to visualize the outcomes of a Fourier transform is this panel on the right. On the x-axis, you have the frequencies of those constitutive sine waves. And on the y-axis, you have the weights of that weighted sum. And so the basic idea is you can do some math to get an expectation of the power spectrum under the null hypothesis of the no cycle OUSS model. And then you look for spikes in this power spectrum that would violate or provide evidence against the null hypothesis. Now, this is a fine test. I like it. It's a good paper, but it's potentially underpowered for two reasons. One is that population cycles have irregular periods. That is, if you look at the time distance between the peaks of a cyclical time series in ecology, that period of time changes because of the noise we were talking about. A severe cold winter could prolong a cycle for several years. And this is going to add noise to the power spectrum. And then two, it's a null hypothesis significance test. Like all null hypothesis significance tests that use a small alpha value, the classic value is 0.5, these prioritize specificity, which put another way, prioritize avoiding false positives. And the trade-off is that we miss true positives and underestimate the overall prevalence of cycles. Now, the focus of this OUSS paper is not quantifying the prevalence of cycles. It's putting forward this new test. But they do analyze a large data set, a large collection of ecological time series in that paper. But they include time series that were sampled both annually and monthly, okay? Now, the monthly sample time series are almost certainly going to demonstrate cycles, but not because of predator-prey or resource-consumer interactions. Instead, those cycles are going to be caused by seasonal forcing, purely the fact that there are less phytoplankton in the winter because it's colder. So for my analysis, I'm going to exclude those. Now, applying the OUSS test to only the annually sampled time series, we see a detection rate. We see evidence against the null hypothesis of no cycles about 6% of the time. Okay, so we're going to do something a little bit different. We're going to fit the simplest possible models that can generate cycles, which in this case is an autoregressive moving average model, with 2 autoregressive lags. So these are just the sort of standard out-of-the-box time series models. And it's easy to understand this autoregressive part. It's like a linear regression, but instead of having distinct variables as response and predictor, you have population density for both response and predictor. It's just that the predictors are used with a time lag. So you use last year's density to predict this year's density. And if you use last year's density and density 2 years ago, then the model can potentially produce cycles. And because we're calculating, or because we're fitting these models using Bayesian methods, for a single population, we can calculate the probability of cycles. Given the parameter estimates of this model, we can calculate the characteristic period, which is 2 pi over the imaginary part of the dominant eigenvalue. And then we can say that those parameters imply that the population is cyclical if the characteristic period is less than half of the time series length. I'm imposing this requirement that the characteristic period be short enough to avoid mischaracterizing long-term secular trends with periodicity. And then finally, the probability of cyclicity is the portion of posterior samples from the Markov chain Monte Carlo or MCMC algorithm that imply cycles. Now we're going to apply these simple time series models to 878 time series from the Global Population Dynamics database. This is a subset from over the 5,000 time series available that pass a number of quality filters. In particular, we're looking at time series with an annual sampling frequency. We're looking at natural non-lab populations, and we require over 25 years of data. And as you can see here on the right, where I'm showing the real-time series and the ARMA simulations, the models do a pretty good job of capturing the dynamics, at least qualitatively. And as a final data pre-processing step, we're going to apply low-frequency detrending, specifically a Gaussian kernel with a 7.5-year standard deviation. Now, this is a very, very conservative way of detrending. A Gaussian kernel with 7.5 years standard deviation is kind of like a moving average over 30 years. So there are problems with detrending. In fact, detrending with a moving average can actually induce emergent cycles in the detrended time series. It's an old phenomenon from economics called the Slutsky-Yule effect. But here we're doing it so conservatively that it's not a concern. And yes, I did simulations to check that out. This detrending really does improve cycle detection. Here you can see a time series of a muskrat. And then on the right-hand side, the posterior histogram of characteristic frequencies. When you do the detrending, the cycles here really pop out, and that's reflected in a lot of positive frequencies, indicating that the muskrat population is cyclical. So good news. These ARMA-based detection methods do much better than the OUSS test, especially when it comes to statistical power. To be completely fair to the OUSS test, it does pretty well when there are 25 years of data. But as you increase all the way up to 200 years of data, that's longer than the longest time series in the Global Population Dynamics database, you get power of 0.25. Now, what you hope for in a null hypothesis significance test, sort of a gold standard, is a power of 0.8. So we're not getting anywhere close to that. And for each population, we get a probability that it's cyclical. But then how do you say whether a population is cyclical or not? How do you convert that to a binary feature? So to do that sort of conversion would require us normally to impose some sort of probability threshold. Oh, a population is only cyclical if it has 0.95%, or sorry, 0.95 probability of being cyclical. And if you do that, then you see indeed about 6% of populations are cyclical. But if you use a less stringent and maybe a more reasonable threshold that a population can be called cyclical if it's more likely than not to have cycles, then 25% are cyclical. So far, we haven't really answered the question, how common are cycles really? To solve that, we're going to use a Bayesian prevalence analysis. So here we have the probability of a positive test result simply expanded with the law of total probability. And if we look at this hard enough, we can realize that we know what the positive test result is. It's 0 or 1 for each of our time series. And we know the probability of a positive test, given that the population is cyclical, because we did a simulation study and calculated false negative rates and false positive rates. So we can treat the probability of a population being truly cyclical as a parameter that can be estimated in a statistical model. And here is the statistical model. The only detail worth noting is in the previous graph, we saw that the error rates changed dramatically with time series length. And so we're going to allow that to happen in this model as well. The false negative rate and the false positive rate depends on the time series length. Now, performing inference for this model, we see that 8 to 25% of populations are cyclical. Now, here I'm showing the posterior distribution of prevalence in this ribbon as a function of the minimum time series length considered in the analysis. Okay, and I'm doing that because in general, in time series analysis, the length of the time series really matters. Now, if you look across this ribbon, when we still have over 25% of the data, the external bounds of the posterior distribution are 25 and about 8. So I'm going to say, embrace uncertainty. The prevalence is between 8 and 25%. But of course, this analysis isn't perfect, and there's potential sources of bias worth mentioning. One is that the extra conservative detrending that we use probably underestimates prevalence. Also, with these time series, you often see this phenomenon of intermittent cycles, where the population will cycle for a bit, and then it'll kind of settle into an attracting equilibrium pattern, and then even go back to cycles. Now, I would say that such a population is cyclical, but the models often say that those populations are not cyclical. So this is going to underestimate prevalence in total. And finally, there may be severe publication bias and selection bias. Publication bias being the idea that only papers with cyclical populations get published. They're more likely to get published. And selection bias being the idea that ecologists only start studying cyclical populations in the first place. Now, I have some ideas about how to address that, but I'm not there yet. And with this model-based framework, you get even more out. You can classify cyclical populations further into noisy or stable variants. So here, each point is the posterior median of the characteristic frequency of cycles in the population, and the noise to signal ratio, easily calculated from model parameters. And where populations fall in each of these 4 quadrants corresponds to the qualitative nature of population dynamics, how they look to the eyes. So if you look at population A, it's got a 0 characteristic frequency and a high noise to signal quotient, indicating that it's a noisy equilibrium. And here you see one of those cases of intermittent cycles, 1 cycle, 2 cycle, 3 cycles, then into attracting equilibrium, maybe a trend here, maybe we're going into cycles here again at the end, it's hard to say. Now, if you sort of go to the opposite quadrant, look at D, a high characteristic frequency and a low noise to signal ratio indicates stable cycles, like those seen in this sockeye salmon population. And we can also stratify by taxa. Here, we're looking at the proportion of populations in each order which exceed those probability thresholds for calling a population cyclical. So salmon, grouse, and forest lepidopterans have a large proportion of populations that are definitely cyclical. And on the other side of the spectrum, here we have ducks. And I guess that's good for the ducks because if you think about it, you don't really want to be part of a cyclical population because there's a 50% chance that you'd end up in the part of the cycle where everyone's starving. So, if you sort of situate yourself behind Rawls's veil of ignorance, then things are looking pretty good for the ducks. Okay, we covered cycles, so now let's go to chaos. Most people think about chaos like this, just a swirling mass. Maybe they think about punk rock. But mathematicians think about chaos like this, sensitive dependence on initial conditions. The idea is that you start out with 2 trajectories that are really close to each other. In the ecological context, this would be like 2 lakes, one with 1,000 ducks and one with 1,001 ducks. And then you track how fast the population densities diverge over time. If they diverge exponentially fast, then you have a so-called positive Lyapunov exponent here, typically denoted with lambda. And that is exactly what chaos is, a positive Lyapunov exponent. And of course, this divergence of population trajectories can't last forever because population growth can't last forever. So eventually they fold back into themselves. And if you have a 3-dimensional system, this folding and crossing looks like a swirling 3D mass. These are called strange attractors, and they have kind of fun names sometimes. This is the teacup attractor from Thomas Powell and Alan Hastings. So a little extra motivation, why care about chaos? Again, it's cool. And I think this merits some emphasis. I sometimes wonder if people would care about chaos so much if it was called something less recognizable, less punk rock, right? What if we called it sensitive dependence on initial conditions, or the acronym SDOIC, right? Then who cares about chaos? Um, another motivation is that it provides a universal explanation for these seemingly random fluctuations. Um, the idea is if you look at an ecological time series, it really seems like a total mess. And yeah, you might be able to find some association between the growth rates and precipitation. You might be able to get that published. But at the end of the day, the R squareds are really low. And when you close your eyes at night, you're haunted by visions of these time series. And maybe you can make it all go away with this simple concept of chaos. I think that's a really powerful idea. And there are potential implications for prediction. Everyone knows that the weather is chaotic. That's why you can't predict it more than 7 days out. And the way meteorologists have improved their predictions is getting better estimates of initial conditions. And if ecological populations work the same way and are relatively noise-free, then maybe we could do the same thing there to improve prediction abilities. But it's really hard to know what to think about the prevalence of chaos. So there are these older comparative analyses with a few dozen time series that find chaos is rare. But then there's a recent analysis that used uh, modern sophisticated methods from nonlinear system theory and found that chaos is not rare, around 33%. But on the other hand, there are few empirical examples of chaos. I was able to find only 6 plausible examples, and 3 out of 6 are microcosm experiments. And then finally, chaos research has been on the decline, which maybe indicates that it's not so empirically relevant, but there's been a possible resurgence in the last several years. So the literature is not a great help here. So let's try to figure it out ourselves. So we're going to apply the new chaos detection methods to the time series database, the Global Population Dynamics database, specifically a neural network model for the Jacobian of the underlying system, using the SMAP model to get the Jacobian of the underlying system, recurrence quantification analysis, and a committee method which combines the previous 3 methods. It just says, okay, the 3 previous methods vote on whether a time series is chaotic, and majority rules. And then we're going to compare the rate of chaos detection in the Global Population Dynamics database to the error rates determined with a simulation study. And then, just like we did with the cycles, we're going to perform the Bayesian prevalence analysis. Now, here's a key. Simulations must be realistic. So for the non-chaotic simulation, I'm using ARMA models again, parameterized with the Global Population Dynamics database data. And the simulated time series will also have a similar distribution of time series lengths as the Global Population Dynamics database. And for the chaotic simulations, I'm using empirically calibrated models from the literature. So here are those models. Here are 5 out of the 6 models, actually. One is a flower beetle microcosm. Another one is New York measles, an SEIR model with seasonal forcing. We have a New Zealand intertidal community, a zooplankton and phytoplankton microcosm, and Fennoscandinavian voles. And as you can see, the models aren't perfect, but they're the best we've got, and they seem to capture a good bit of the behavior of the original time series, and they're definitely chaotic. All right, putting that all together and performing the Bayesian prevalence analysis, we get the main result, which is chaos is probably rare, but there's a lot of uncertainty. So using the committee method, which is the best, we see that 18% of the time series in the global population dynamics database test positive for chaos. But then the error rates are high. The false positive rate is 20%. The false negative rate is nearly 40%. Combining this all in the Bayesian prevalence analysis, you get a posterior distribution of prevalence of 0 to 16%. And here in this figure, you see the posterior distribution. All right, so it's really hard to estimate the overall prevalence of chaos. But what about individual time series? Maybe we could really limit the false positive rates such that we could identify a couple time series, maybe exceptionally long time series that are definitely chaotic. So the problem that we're going to overcome here is that we can't use model-based estimation because there's no standard phenomenological model that forces or that can be both chaotic and non-chaotic. So we're going to use the standard phenomenological non-chaotic ARMA models that we've been talking about to create a population-specific null distributions for the outcomes of the chaos detection method. So we're going to fit ARMA models to real-time series, and then we're going to simulate 1,000 time series from that definitely not chaotic model. And if the real-time series has a positive test result in the form of a positive Lyapunov exponent, and X% of the non-chaotic series have a negative test result, then we'll say the original time series is chaotic. Now, X here is a quantitative threshold. It's a tuning parameter that we can tweak to control the false positive rate. So here you see the results. As you increase X, the percentage of non-chaotic simulations that test negative for chaos up to 80%, you see that very few series in the global population dynamics database can be classified as chaotic. But what does that really mean? Well, if we look at the so-called receiver operator characteristic, which plots false positive rate against true positive rate, we see that we are indeed able to control the false positive rate, getting it down to that standard 0.05 level. But then we have virtually no statistical power. The true positive rate is pretty much 0 here. So this method is unable to detect chaotic time series. But it's not necessarily saying that they don't exist. It's just saying that the method doesn't work to detect them. This reinforces the idea that it's just really hard to detect chaos. And if you look at the 3 time series here at the at X equals 0.8, then at least 2 out of 3 of them appear to simply be testing positive for chaos because they have a trend. So is that chaos? I would say not. So now we'll probe why chaos is hard to detect with a causal analysis. So we're going to make adjustments to the simulations, and then we're going to look at the difference between the hypothetical worlds between the adjusted and realistic time series with respect to the chaos detection error rates. So here are the results. There's a lot here, but we're going to walk through it. On the X and Y axes, we see all possible pairs of adjustments. And the values, the numbers, are the false negative rates of the adjusted simulations, and the color indicates whether or not the adjusted simulations do better in terms of detecting chaos. So here we see if we make the time series longer and we eliminate observation error, then the false negative rate falls to 0.06%, or sorry, 0.06. That's really good. But interestingly enough, if we don't eliminate observation error and simply make the time series longer, then chaos is even harder to detect. And an implication of this is that more data collection is not going to help us detect chaos, at least very much. So here's a more detailed chart showing how the false negative rate for the chaotic simulations changes with time series length. Now, keep in mind the longest time series that we're considering in the Global Population Dynamics database is a little over 150 years old. So by the time we get to 250, there's still pretty significant false negative rates here. All right, to wrap it all up and get to the discussion, cyclical dynamics are slightly more common than previously thought. And unsurprisingly, salmon, grouse, and forest lepidopterans are often cyclical. And then chaotic dynamics are probably rare, but we don't really know. There's a great deal of uncertainty due to the interaction between the intrinsic nature of ecological time series and the chaos detection methods. Observation error plays a big role. And while we might be able to reduce that, there are logistical and funding constraints. And process noise, or intrinsic stochasticity, also plays a big role, and that's never going away. All right, so I had some sample discussion questions, but it looks like we only have 20 or so minutes left, so let's just jump into the discussion, and thank you all for your time.
Thank you so much. That was a great talk. So, as usual, if anyone has a question, please raise your hand in the participant list and I will call on you. Any takers?
I don't know how to raise my hand.
Then please go ahead.
Thanks, Evan. That was an interesting talk. I really especially enjoyed the first half. With regard to the second half, I think it's probably pretty important to recognize that a lot of the conclusion that chaos is rare comes from the false positive rate that we estimate using the ARMA surrogates, right? And so, as you and I have talked about, we know that theory shows that you can reconstruct any finite time series exactly, right, with a linear model with noise. And so, if the series that we're reconstructing is a chaotic series, and then we apply a chaos detection method to that, and it says that it's chaotic, well, that's not really a false positive. That's actually the right answer, right? And so I think then the question becomes, how often does that happen when we simulate ARMA series that were based on, say, a true underlying chaotic system? And so I did that just yesterday because I was kind of curious how this would turn out. And when I do that, so I start with a known chaotic system, fit an AR model to that, then generate a whole bunch of ARMA circuits and ask how often they come up chaotic. The answer is about 50% when the time series lengths are, 50 points or less, if the ARMA model fits well. If the ARMA model doesn't fit well, it's generating things that don't look like chaotic time series, and the apparent false positive rate is less than 10%. And in both cases, the false positive rate drops off exponentially with time series length, which is exactly what you'd expect from theory. So starting from a chaotic system, I get results that are entirely consistent with what you got for the global population dynamics database. Mm-hmm. And so I suspect that our false positive rate estimate is inflated, possibly quite a lot. At least, it would be 100% based on my stupid simulation, which I just did yesterday. So in fairness, there's far more exploration needed. But in the end, I think maybe the most important thing here is that we should focus on the practical things about whether or not dynamics are unstable, rather than getting hung up on what to call it. Anyway, so I'm wondering what you think about this trying to ballpark the false positive rate using a known chaotic simulation.
Sure. So I think what your simulation analysis shows is that it's really hard to detect chaos. I'm not sure if it shows that the false positive rates are inflated because we're using these ARMA models that are constrained to be similar to real time series, and the ARMA models do a pretty good job. The ARMA models have a good predictive performance several steps out in comparison with more complicated methods like the SMAP. Now, you mentioned that maybe Koopman or Fourier theory shows that a linear model can approximate a nonlinear chaotic model pretty well. But the ARMA models I'm considering have a pretty small number of lags, usually 1 or 2, sometimes 3 lags are selected. Okay, and then
that's what I did too, actually, for my little simulation test of your simulation approach. I only used an AR3, and so I get false positive rates that are about apparent false positive rates, which are clearly correctly positive about 50% of the time. So I think you and I probably need to go back and forth a little bit more about what constitutes a false positive.
Sure. And then as far as further analysis goes, this isn't a complete analysis. So I'm going to be looking at other things with you, Steve, including non-chaotic null models created by phase randomization. And but I've already done a ton of robustness analyses, and the results are looking pretty stable. And then as far as the practical aspect of this goes, I think what this shows us is that it's really hard to say if chaos, or if a time series is definitively chaotic or not. But personally, I think there's value in the concept of locally appinative exponents, which shows you whether the close trajectories diverge or shrink towards one another over short periods of time within a time series. And this gives rise to this idea, it's not my idea, but I forget who to attribute it to, of pockets of predictability, which implies that ecological dynamics may be far more predictable in some years or periods of years than others. I think that's a valuable insight.
Oh, thanks. No, I'm not thanking you for the insight. I'm thanking you for the response to the question.
Thank you so much. Sean, please go ahead.
Hi, everybody. This is my first time at one of these things, but thanks, Evan. Really interesting talk. Can you hear me okay? Oops.
Yes.
Yep.
Okay. So I'm like looking at that initial presentation of the model. It looked to me like you were not explicitly including observation error. Is that right?
I didn't include it in the exposition, but
Yeah.
observation error is one of the ARMA model variants that I'm looking at.
Okay, so I was curious about like to what extent the incorporation of observation error may make your tests for cyclicity more or less conservative, just because in earlier analyses of the GPDD, just whether you detect density dependence at all, particularly going time series by time series, depends a lot on whether you try to include observation error. Second question is, the follow-up question there is really, to what extent could constraining the magnitude of observation error, for example, just by counting twice, improve our ability to detect some of this complex population dynamics, as opposed to waiting 20 more years for more data? And then the other question I had was really about the distribution of stochastic fluctuations in the system. I mean, I work on systems where you have, possibly almost a bimodal distribution of little r's, where you have a catastrophic event in one year and there's a wildly different little r. So I was wondering if you could maybe talk a little bit about that as well, the extent to which the assumed versus real distribution of, say, fluctuations in population growth rates might make it hard to detect some of these patterns.
Okay, so on the topic of observation error, I've recreated this graph on the right with a whole bunch of different model structures here, including ARMA to Q models with observation error, and these curves don't really change much. And on top of that, in this Bayesian prevalence analysis, that should partially account for additional misses in cycle detection due to observation error. Because yeah, the rate of positive tests is going to go down potentially, but then the false positive rates and false negative rates in the simulations with observation error are also going to change. One thing that I've wanted, so I have noticed in these model fits that there's correlation in the posterior surface between the process noise and observation error parameters. That's pretty unsurprising. And observation error does seem to be larger than more detailed studies have found. I think more detailed studies find that it's like between 0 and 15% of the total variation and population abundance on the log scale. And so I didn't include observation error in this figure because the observation error also often had like bad model fitting diagnostics. But I might recreate this figure using a stronger prior for observation error scale, as indicated or as evidenced by those previous studies. And then maybe I would get better model fitting diagnostics. So on the distribution of stochastic fluctuations, yeah, you can very clearly see those in the time series. And the models don't account for that at all. The models assume Gaussian process error on the log scale. There would be a couple ways to look at that. One is just adding another parameter to the model, modeling the noise distribution with the t distribution. And the degrees of freedom parameter there can interpolate between Gaussian error and a Cauchy error. Another one is to allow the Gaussian noise parameter to fluctuate in an autoregressive way over time. Those are called Garch models in economics. But I haven't done either of those things yet.
Thanks.
Thank you so much. And I think, Steve, you had your hand up, so please go ahead.
Hi, Evan. Thanks for a great talk. I have a couple of things. Offline, because no one but you and me would be interested. I want to talk to you about your neural net fitting, because I found that you had to really work hard to avoid false positives, but it was possible to do it. So there may be, and your rate was a lot higher than what I was getting way back when. But like I said, you had to work really hard to make that not happen. And about the difference between your ARMA simulation results and Steve Munch's, I wonder how much of that has to do with the stability of the ARMA model. That is, that if you've got an ARMA model whose Lyapunov exponent is really, really negative, maybe you're not going to get false positives. And if you're getting your ARMA by fitting it to a chaotic model, maybe you're getting an eigenvalue, a Lyapunov exponent that's close to 0, and that'll give you a high false positive rate.
I did think of that.
Okay.
And they're all stable. So all the ARMA models are stable. They're just close to the chaotic series. And the chaotic series is very close to something that's periodic. So it's possible. My point was just that it's very possible to inflate the false positive rate.
Yeah. And so what this is leading to, Evan, is the idea that maybe instead of doing your analysis, that the one with a false positive, false negative, we're not looking at that slide, but maybe you could bring it back where it's the one with the Bayesian. Yeah. The one you had just a moment before with the false positive rate.
This is for cycles or chaos?
Chaos, for chaos, right
chaos,
here.
Okay.
Yeah. Whichever one.
We'll get there.
Yeah, we'll get there. Okay. All right, keep going.
Oh, not this one.
Not this one. No.
Do you want the math?
The one with the math, yeah.
Okay.
But okay, yeah, this is it. Okay. That maybe it would be worth not thinking about it as positive or negative, just scoring the Lyapunov exponent as either it's chaotic or not, but thinking about false positive rates as a function of what you actually observe. That is, if you estimate a Lyapunov exponent of plus 0.2, what's the chance that that's a false positive? If you estimate one of plus 0.05, what's the chance that that's a false positive? And sort of look at things more on a case-by-case basis rather than lumping all the positives together. Maybe you'll find more examples where things are estimated to be so strongly chaotic that it's unlikely to be a false positive.
Yeah, so that's an interesting idea. So like Steve, all of my simulations, ARMA simulations, are stable. And that's because I'm using this trick by Jones, 1987, in the Journal of the Royal Statistical Society C. To pick the prior distribution of autoregressive parameters such that it's always stable. But I think you're onto something. Like, instead of having false negative rate or false positive rate depend on time series length, maybe it depends on the dominant eigenvalue of the ARMA model. Is that sort of what you're suggesting?
Yeah.
I
Also
think that's a good
suggesting that
idea.
the false positive rate might depend on what your estimate is.
Mm-hmm.
Okay, so that if you've got an estimate of plus 0.002, that has a good chance of being a false positive. But if it's plus 0.3, then that has a lower chance of being a false positive. And you might get different results if you looked at things that way.
Gotcha. Yeah. I will do that. That is a good idea. And as far as the neural net goes, I'm using maybe this is cheating. I'm using the dchaos R package, which has a lot of fine tuning going on behind the scenes.
Okay, I'll take a look at that. Thanks.
Thank you so much. Are there any other questions? Yes, Chris, please go ahead.
Hi, yeah, thanks for that. It's really interesting, actually. One thing I was wondering a little bit is you've got these predictors based on the taxa for whether there's cycling or so on. Have you been able to pick out any predictors? I'm particularly thinking in terms of the environment that these time series are coming from, that seem to indicate getting some chaos. Because we should really be able to build from the bottom up to be able to predict when this chaos is happening. I'm not saying it's going to be easy, but there should be some sort of drivers that when you get chaos, when you don't. And if you are able to pick them up, that might lead to more confidence there's actually a fair bit of chaos kind of about. So has there been any predictors that kind of explain, even if it's only the likelihood of a chaos label, even if you're not confident it is actually there or not?
Sure. 1 second. Okay. So first I'll talk about cycles instead of chaos. So a great or actually no, I'll talk about chaos instead of cycles. Okay. So the two predictors that I'm aware of is the probability or the probability of testing positive for chaos increases fairly linearly with the probability that the time series is cyclical. So the cyclical ones tend to look chaotic, and the cyclical character of chaotic time series shows up in the like 3 empirical non-lab based examples of chaos that we have in the intertidal community, I think Benicia 2008 PNAS, in the Fenno-Scandinavian voles, which is a Turchin and Elner paper, and one other, the New York measles. And so I think that is a real pattern. The probability of being positive for chaos also increases with time series length. There aren't really any notable patterns, any differences between orders that can't be explained by time series length. Yeah, and as you know, it could be that real
that's
chaotic.
not true.
Sorry.
That was Stephen jumping in, and not me. I didn't.
Sorry, keep going.
Oh, Steve wants to say that phytoplankton or maybe zooplankton are more likely to test positive for chaos. Is that right?
So the generation time of the critter was really pretty strongly correlated with the Lyapunov exponents. So as an external indicator of something being possibly chaotic, short generation time things are far more likely. And you could write this off as a time series length kind of thing. But if we're asking about external predictors for what might be chaotic, I think that's not unreasonable.
Sure. And our analyses differ, so we might get different results. Now, the fact that real empirical examples of chaotic systems tend to look cyclical, it could be just a general feature, or it could be that chaotic systems with a more aperiodic character that kind of look like the logistic model, that those are being hidden by spatial averaging. So the idea here is to imagine a bunch of weakly chaotic subsystems. If the spatial scale of sampling is larger than the spatial scale of dispersal, then we'll be basically averaging over all these weakly coupled chaotic subsystems and losing the signal of chaos. So it could be that the real chaotic systems always look kind of cyclical. It could be that the non-cyclical looking ones are just hidden from us. Vadim?
Hey, thank you. Good to see you. Very nice talk. Yeah, the setup was beautiful in the cycle section. The chaos part went by a little bit too fast for me, as someone who doesn't regularly work on detecting chaos. I was basically just kind of had a follow-up with if we have kind of uncertainty, or have you looked at what kind of overinflating the false positive rate, overestimating or underestimating it would do to kind of the follow-on napkin calculation of the modal proportion of time series that are chaotic is 0. I guess, in other words, like when we have like some methods finding 30% of the time. So like when we have different methods finding very different answers, and we're kind of working out what the right way of looking at it is. And kind of your main emphasis was that chaos is really hard to detect. Like how big of confidence can we have in the modal proportion of time series being chaotic that it's actually 0, versus just going away with the one takeaway that we don't know, or we're not sure.
Yeah, partially, I don't think so much emphasis should be placed on the mode. And it's because for the chaotic Bayesian prevalence analysis, I'm not stratifying by time series length like I am for the cycles. And I'm not doing that because the chaos detection rates don't appear to change very much with the range of time series lengths in the global population dynamics database. It changes a little bit, but not much. And so when you have that sort of simplified Bayesian prevalence analysis and the false negative rate is larger than the false positive rate, then you always get the mode at 0. So I don't think we should put too much emphasis on the mode at 0. On the other hand, I think this is the best way of doing the analysis to date, and so it's the best answer we have. I do think you're onto something. It's worth sort of tweaking the false positive rate a little bit and seeing how much the numbers change. I think that could be a valuable exercise. Does that answer your question?
Yeah, thanks.
Maybe I missed part of it. I'm not sure how many parts of the question there were.
Well, if you feel, Vadim, that there's some other part to the question, let us know.
Yeah, no, I think that, yeah, I'll need some time to absorb some of this, yeah.
Thanks. No, that's good. Any other questions?
Yeah, it's always tricky when you want kind of a takeaway number for the prevalence of chaos or something, and then
Yeah.
we're not sure. It's hard. It's a hard takeaway to pitch.
Yeah. So the main difference, since we've talked about it so much, the main difference between my results and the Rogers et al. Results, the paper that Steve is on, is that their false positive rates were generated, or their false positive rates were generated with often linear non-chaotic models.
That's
So
not quite.
not all of them, but so for example, there's an AR model. And the way I do things is I fit the ARMA models on the log scale of abundance. And so when you take the Rogers et al. Simulations and take the ones that could plausibly be like exponentiated, and that would be a plausible ecological model, you actually see that their false positive rates are very similar to the ones that I observe.
Are there any other questions? Well, then, thank you again, Evan, for the great talk and the great discussion. And thank you, everyone, for joining in. The next seminar is going to be on the 14th of May. It's going to be Mike Wittmann talking. So hope to see you then. And until then, have a good rest of your day, rest of your evening, wherever you are, and see you soon. Bye, everyone. Thank you.
Bye-bye.